cosmos and all of its galaxies of stars and planets are part of an intricate design shaped by something that's been eluding scientists for decades.
The hunt for dark matter is going on worldwide. We haven't been able to see it. It's invisible to us. We're not sure exactly what dark matter is at all.
We have built massive machines on top of mountains
Our laboratory is the observatory.
and below Earth's surface to explore.
It takes imagination. Imagining what that dark matter might actually be, and then design a detector, design an experiment around it.
And now, a technology way ahead of our current capabilities brings us to the point of greater understanding.
If we can interact with it, fundamentally this is really important to our understanding of where we are in the universe.
A dramatic advancement in the hunt for dark matter has begun.
We're trying to piece something together that's very hard to see because it's dark matter. There's a good chance it's made up of particles. These particles were produced in the very beginning of the universe in the Big Bang, and they've been around ever since. So now my gut feeling tells me there are particles out there we can detect.
Scientists describe two phenomena that emerge at the time of the Big Bang. Dark energy, the force that has caused the universe to expand for about 14 billion years. And then dark matter, the substance that has provided structure to everything within it. Both are deep mysteries yet to be proven. Because dark matter is so elusive, scientists are attempting many different experiments to find it. One experiment involves trying to create particles of dark matter.
As soon as we know we can make it, we can design machines to study it.
Joe Candela and his colleagues at the University of California at Santa Barbara are part of a multinational effort to create new technology that is unimaginable in scale. The technology they're building is a particle detector called the High Granularity Calorimeter, or HGC.
The High Granularity Calorimeter is a 6 million pixel camera. It has to be capable of taking images every 25 nanoseconds. For anyone who's played with cameras knows that this is utterly insane. This is the highest resolution, slow motion camera anyone's really kind of built.
They're essentially building a detector that's like a camera that can record and process 10 terabytes of data per second.
That's something like a 1,000-word essay by every human being on the planet every second in terms of amount of data. Our electronics engineer pointed out this is more than the entire internet worldwide will be producing in 2018.
The HGC will have 22,000 silicon wafers. It will eventually capture 2,400 times the data per second over the existing detector, increasing the odds of finding dark matter.
The tasks I was given directly were to manufacture some of the first generations of what we call the module PCB.
PCB stands for Printed Circuit Board. This is the basic component of the HGC, which is multi-layered in its construction.
On the underside here, we'll have a silicon wafer that'll come in and sit under the PCB. And wire bonds will go from the top surface, from each one of these small golden dots, down to the PCB underneath. And that will be how we host the two major important components. That's the sensor and the front-end electronics on top.
Designing the HGC began with an idea, but it did not come with a set of schematics on how to build it.
Oh, that's why. It was like, here's a sack of parts, and those parts need to fit in this space, and you gotta play Tetris till it works.
Believe it or not, probably the thing that's giving us the most trouble is finding space to get the cables out of the detector. There's very limited space. When you build a big detector like we have at the LHC, you don't want cracks. You don't want places where particles could not be detected. So you design these things to be very hermetic very well sealed. That means there's very few places cables can go, and the spacing for the cables is very tight. And so that's actually a big problem for us.
The team at UC Santa Barbara is collaborating with a team at CERN, the European Organization for Nuclear Research located in Switzerland. CERN houses the largest high-energy physics experiments in the world. The target for the high-granularity calorimeter is the Compact Muon Solenoid Detector, or CMS. This 15,000-ton science experiment, buried 30 stories below ground, helped find the Higgs boson in 2012.
At the moment, in our experiment in CMS, we have devices now in that region that at each side is a 10,000 pixel camera. We're going to replace those sides with 3 million pixels each, and we're going to design a device that will actually allow us to have capabilities we've never had before.
This increased resolution will allow scientists to see billions more particles produced by the Large Hadron Collider, making it harder for dark matter to hide. Jim Straight is a particle physicist who's part of the team to integrate the new technology into CMS in the hunt for dark matter.
My big job is to help coordinate the overall technical design of the new NCAP calorimeter.
The NCAP calorimeter is a key component for finding evidence of dark matter.
The detector, of course, can be opened like an accordion into various slices, which allows us to get at the existing NCAP calorimeter. What we have to do is make a new calorimeter that fits into exactly the same spot.
I would say that the detector we're building now is an order of magnitude more difficult than any detector we've built before. Not necessarily in terms of what the basic components are that go into it, but in the way it's built and the compactness of this device is different from anything we've ever done before.
Overall, the biggest challenge in this is figuring out how to get the signals out. We're building a device that has 6 or 7 million channels. And you have to bring in power and other signals that control how the detector works, all inside the same space that is already there, without compromising the performance, density, and coverage of the detector itself.
Experimental physics on this scale is a result of another branch of science, observational astronomy. It is astronomers who figured out the presence of dark matter in the first place.
There's two reasons why we believe dark matter is important and exists. Firstly, we feel its presence from its gravity. So the motions of galaxies in clusters of galaxies, we know that those motions are governed by something that's very, very massive that we can't see. Secondly, gravitational lensing, the bending of light by massive objects, enables us to chart how much dark matter there is and also where it is.
Astronomers, like Richard Ellis, search for visible proof that dark matter exists, in this case, on a mountaintop on the island of Hawaii.
The romance of going to all these remote mountaintops, building these wonderful machines, is an example of something our civilization does supremely well.
At nearly 14,000 feet above sea level, the dormant Mauna Kea volcano on the Big Island of Hawaii is home to some of the largest telescopes on Earth.
Just think every night when you go to sleep, there are dozens of astronomers all over the world beginning to work, making their observations. Astronomers have a variety of telescopes for looking at dark matter. We're here at the Keck Observatory. This is an optical ground-based telescope. We have a partnership basically with the Hubble Space Telescope. particularly in the area of gravitational lensing. So what you're seeing in this image at a stroke is the tremendous power of gravitational lensing. A huge foreground cluster with lots of dark matter is distorting and magnifying large numbers of background galaxies at various distances. But then you can see this red arc here that is very, very nicely illustrated. It's about 3 times further away than the cluster. And you see there are multiple images. You see the same light of the galaxy, the distant galaxy, seen in different places. So it's like a mirage. So this opened up the way of studying dark matter thanks to Hubble.
While the Hubble Space Telescope can gather extraordinary detail from space, ground-based telescopes provide a bigger picture. Dr. Ellis uses the Keck telescopes to measure the distances between Earth and the galaxies themselves, to interpret the influence of dark matter on the structure of the universe.
What we're trying to do is provide those key distance measurements through analyzing the light of these background galaxies.
This 300-ton telescope with a 10-meter mirror is being positioned for tonight's work to look into the stars. Dr. Ellis and 2 students are in communication with a technician.
Okay. We're setting everything up here for tonight's observations, and fingers crossed we're going to get great data. You could say dark matter is something of an embarrassment. First detected in the 1930s. We have told often that we live in the golden age of astronomy, and yet here we are 80 years later and we don't know what it is.
Because it's 85% of the known matter in the universe, and 95% of the universe is not known to us. For experimental physicists, that's a pretty bad record. We've spent centuries, we have this incredibly detailed understanding, but it's only of 5%.
It's 1, 2, 3, 4. There's 4 pixels. It's like 4 pixels in the blue as well. That's amazing. The idea of discovering the nature of dark matter is funding effectively very big advances in instruments, both in physics and in astronomy. All of these are driven by the mystery of trying to solve the fundamental question of what is dark matter, why is it there, and why is it so important in understanding the history of the universe.
Fritz Zwicky, a scientist from the California Institute of Technology, came up with evidence for dark matter in 1938 while studying a galaxy 20 million light-years away. He concluded it could not have formed into a spiral without additional gravitational support. But it wasn't taken seriously until nearly 40 years later, when 2 scientists from Carnegie Institution, Vera Rubin and W. Kent Ford, did measurements of spiral galaxies that led to the conclusion that dark matter was essential to the structure of the universe. Finding it means we can begin to confirm centuries of theories, but even more, discover new ones we could not before imagine. The high granularity calorimeter is a big technological leap toward reaching this goal. It will be a huge task to mass produce the thousands of elements that make up the entire system.
UCSB is responsible for establishing the methodology for building them, to basically set it up, establish the kind of tools that are needed, all the procedures, the equipment, establish how to do this, and then we will transfer that capability to 4 or 5 centers worldwide that will do most of the production.
We specifically are working on developing an automated assembly process for the sensors that will go in the ℏ-𝐞. The HGC is a huge, huge project. We're going to be making 22,000 sensors.
This silicon-based sensor has an intricate design to capture particles. Its 6 million detector elements will be linked via microscopic connections.
This is a pattern we have taken a lot of time to develop. You'll notice that there are many circles. Each one of these circles will surround one of the openings in the PCB. Once assembly has been completed on a robotic gantry, we bring it over to the wire bonder. The wire bonder will make the actual bonds from the sensor to the PCB, and from the PCB to the onboard electronics, which digitize the signals that are created from the particles passing through the silicon.
Once I get it, I have to attach wire bonds between the silicon layer and the PCB. We take 25 micron aluminum wire and we use ultrasonic energy, and it kind of vibrates the two materials and it kind of fuses them together so that we can have talking between the silicone and the chip. It's really, really thin, and it's wound around either a 1/2 inch or a 2-inch spool. We have to use a microscope to lead it through each of the wedges, and that takes a lot of practice and a lot of frustration. Once we write the program and set it up, then we can send it off and nobody else has to do that. So we go through the hard labor and then let them just use our program.
But before the high granularity calorimeter goes into full production, the teams have to make sure it works. Testing at CERN provides an optimal high-energy environment to create dark matter particles.
Dark matter is going to be a very interesting search because, by definition, dark matter is different from the usual matter. It doesn't interact. Not interacting means it's invisible. On the other end, if it gets produced and it flies out, it's going to carry with it energy.
If dark matter is made up of particles, then the Large Hadron Collider can produce it. The collaborative work to build and design the HGC includes testing under high radiation conditions. Dave Barney is a physicist and project manager at CERN. He is responsible for the testing.
This hall we're in is one of a couple of facilities at CERN that are almost exclusively for testing prototypes. The beam starts in Switzerland with a bottle of hydrogen gas, which is stripped of its electrons, and you just get left with protons. Then they go into a circular accelerator and then another circular accelerator. So the main one we use, called the SPS, Super Proton Synchrotron, is in itself an extremely powerful device. So this makes the protons go extremely fast, very close to the speed of light. When those protons reach top speed, they're actually extracted and they're sent down a tube and they hit a target. And a spray of other particles comes off of that. Electrons, other protons, particles called muons, pions, and then send those ones down this line into our experiment. We've always been kind of pushing the boundaries of what is capable in electronics technology and detector technology. This device needs to survive at -30°C in a massive radiation environment for 15 years with no maintenance.
The radiation comes from CERN's Large Hadron Collider. It has a system of superconducting magnets that guides particles around its 17-mile system at near the speed of light.
When a particle travels through it, the detector generates some sort of signal that then electronics amplifies and stores if necessary. So we're testing at the moment 8 of these in a beam here at CERN. We've tested up to 16 of these in a beam at Fermilab in the US. And we're trying to understand whether they perform as they should. This module is actually composed of several layers, starting from a plate that sits on top of this copper plate that supports the whole thing. And then it has the silicon, and then it has the printed circuit board on top of that, and they're all glued to each other. Our prototype is based on these hexagonal silicon sensors that are divided up into smaller hexagons. Mostly, there are some funny shapes around the edges, but they're mostly smaller hexagons. So each of these smaller hexagons is an individual particle detector, if you like. And we're testing some of these in a beam at the moment.
The conditions at this beamline area are similar to conditions within the compact muon solenoid detector. This is a critical phase in the development of the HGC. The stakes are high because this project will take 8 years and cost millions of dollars to complete.
To find those elusive few things that might be really interesting, we need an unprecedented precision of our detectors to disentangle between the boring stuff, the stuff we know about already, and the really interesting new stuff. That's where this sort of detector comes in.
As predicted, the high granularity calorimeter is proving to be a great success, capturing particles in a wide distribution of energy ranges, moving us closer to unlocking the deep mysteries of the universe.
Dark matter is something that really takes us to the next step. And so it'll be a wow moment, no doubt about it.
Most of what we were doing so far was to check that we had a working concept, make sure we weren't going down the wrong road. We've already collected data on a stack of 16 modules at Fermilab, a stack of 8 modules at CERN, to test some of the absorbers and get some of the first statistics back already.
This detector has incredible capabilities. It's also extremely challenging to design and build and handle all that data. But if we can get it all to work, this will be, I think, somewhat revolutionary for the field.
When the 22,000 silicon wafers are completed for the HGC, they will reveal particle showers in greater detail than ever before. And maybe, through this, we will find dark matter.
If we find it or don't find it, it has an impact on our understanding of particles in general. We think it has to be particulate, it has to be out there, has to have some interaction with our universe. If we can't make that connection, we have to go back to the drawing board and try to understand what it is and how the universe was formed.